All right, everybody. So, oh, this is annoying. Zoom. Okay. So we're going to be finishing this part of the lecture. I think there'll probably be a part three as well. There's some other things I want to make sure we cover, but we'll just have to wait and see. Let's see. So let me go in. Okay. So the first thing I just want everybody to think about is if there's any topics you specifically want to make sure we cover. I know I had put on the syllabus some things about like some specific nuclear training or procedure things, as well as cybersecurity, or I might have put explainable AI on there. I can't recall. So if there's any topics you specifically want to make sure we cover, let me know or post in the Slack, and I'll make sure we uh, fit those in on a lecture or two. Um, Also, I will have something posted about the final by Saturday night. If you don't see anything by there, then feel free to hassle me a little, so we can kind of talk about that. That is one part. I didn't see anybody comment specifically on the idea I had before about assigning you all each other's topics. Let me know if that sounds interesting or sounds like it sucks or whatever. Um, that's one of the more interesting ones that I had. So let me know what you think about that. And then let's see, going through this 1 second here. Okay, so let's see. Okay, there's the lecture. So Shirley, okay. Yeah, so on the intentionality of error, that's kind of one of the things that happens when you've spent too much time dissecting causation and action in philosophy classes. You end up really looking at, the actions we take as their separate components and kind of how that process is through. But I found that kids, especially either if they're neurotypical or like the student that you give therapy for, are very uh, interesting on how they perceive those things and how they process it, and just the honesty of their own awareness. I think as we become adults, socialization or whatever happens, and we have to know, or we try to lie or make sense of things. Where kids will just straight up say, I have no idea. Um, Cultural values and how that impacts cognition. I guess I'd wonder what specifically you mean by cultural values. Um, I don't know of any research that's been done in terms of like cognitive performance and how if that changes via culture. I wouldn't assume that memory or attention or those kind of things wrong. Um, and human error, again, because it's kind of one of those unintentional things, I would think that human error operates similarly across cultures, but I don't know. That's an interesting question or an area of research there. External feedback loop. So a feedback loop is when you take an action or something, a stimulus occurs, there is a response, and then there's that response then generates its own stimulus, which then there's a response for. That's the loop component. So an external feedback loop would be, okay, you walk up, let's say you're in some fancy new building, novel architecture everywhere. But the doors don't have handles or something, right? What we would do is try to interact with the door in different ways. And then the feedback we get from the door, which could be, did our action work or not, those kind of things. That's the loop we're looking for. Reason in the Norman models. So that's one of those things that I think in nuclear, at least, it's generally considered reason, or you could just refer to it as slips and lapses. That's the other big one that I've heard it referred to as. So, because I'm not sure, like I said, who came with the first, or if there was, if that's a concern there. So, if an operator has a bad feeling or sees something that is wrong, they elevate it to the senior reactor operator, and if they have a question there, they can, they then start to process that, or involve the shift technical advisor, or there's a lot of other steps there. But one of the biggest things to come out of like Chernobyl specifically, which we'll get into that a little bit here, and organizational failures is the idea of safety culture. So one thing you'll hear about a fair amount in nuclear is the concept of a stop work. So a stop work is literally you say the word, we need to do a stop work, and depends on where you work. At the INL specifically, it's kind of a paperwork intensive process if somebody calls for a stop work. But the idea of a just safety culture is that you would never be penalized or anything for a stop work. But that's an instance of that. That's where everything stops until whatever the concern was that triggered it is resolved. But and how often it happens, I'm not sure about. The important thing to remember is nuclear reactors are like carrier ships or like elephants. Like they're these big lumbering things. They're not agile. They don't make fast adjustments. So which part of that is what makes them so safe. I wouldn't assume that we'd have that many instances of things going wrong that they don't know about, or that they're not expecting. There's such complex systems, and there's so many sensors on things that I think that most of those instances you'd be aware of. Okay, and yeah, I've seen that phone number generator thing before. There's some awful design out there. The Demon Core stuff's funny. I remember that, or reading about that. There's yeah, you get back to the 40s and there are a lot of uh really unfortunate instances of these kind of nuclear accidents just because of how little we knew about what was going on then. Let me see what the comments are. Yeah, I've heard about Fat Man and Little Boy too. I have not seen that. Um, it's really interesting. Know a lot about that stuff. Yeah, the conveyor belt. That's funny. Um, yeah, so building stronger doors for the cockpit. It's one of those things. Human, yeah, human factors does come up a lot with tragic events, and I think part of the problem with that is traditionally human factors is not considered during early stages of design, or it's not given its kind of spot at the table when these systems are being designed. Um, it's just not. We see this sometimes on different experiments where the idea of an interface for some system is really not important. It's something they push off to the end, and that's the problem. That's something that you struggle with that. In human factors, I think aviation does a pretty decent job of it. And NASA does an incredible job of it. NASA human factors is everything, if human factors is a verb. But yes, and it's one of those things like so hard to plan or come up with a plan that can prevent the event. Not necessarily. It's expensive to come up with that, and it's experimental generally. So this is a thing that happens in cybersecurity with red teaming. So you can hire. I mean, if you're trying to test the actual code of a system or those kind of the architecture of it, you can hire penetration testers that will try to poke holes in your defenses and things like that. Or you can hire full-blown red team, or you hire an external entity usually to try to either do physical penetration testing, so try to actually break into a structure or building or something, or they can just try to test what weak points there are. There's a lot of really interesting YouTube videos on those on red teams, and you'll have a lot of really interesting takes on those kind of engagements, which are interesting. So you could totally red team a lot of those things where you could just hire people to. Actually used to consider this as a job once. I was thinking of it like a business. Like I don't want a red team like necessarily like security specifically. I mean, it's an interesting field and everything. I just want to try to break things. That's kind of always been my like, hey, can I figure out how to do this wrong and break it? And how would that work? That's kind of an interesting thing. But you could red team airplanes. You could do it all. Nuclear, we don't tend to red team very much because of a unique security thing. I think it's pretty much unique to nuclear. So those of you that have ever been out here at the lab or will one day be out here, there are certain areas where you will see signs that say like uh, lethal force, use of lethal force or use of deadly force is authorized. Um, that is so we talk about this with security at nuclear facilities here at the INL or at power plants. They do testing activities. They're called force on force. So you'll pick a section of your guard force to do different testing or try to sneak into the fence or whatever it is. But it's hard. It's different than normal red team. So usually when you do a red team, your chief technical officer or something will know about it. They won't know how the people are going to try to break in, but they'll know that somebody is. And there's usually some documentation that authorizes the action and those things. In nuclear, uh, so we'll sometimes refer to it. Nuclear security, what they're called protective forces, have zero mandate to save life. That is not their priority. They are so you could not red team a nuclear facility unless you wanted those red teamers to die, because they will shoot first and ask questions later. The priority for them is the security of nuclear material. Period. If they can do that and then help some people, great. But their priority is to secure the nuclear material. So that worked out at the lab back when we did some fuel reconditioning and stuff, was once trained on a security topic. And they said, if there was ever a hostage situation, no one's getting out alive because they don't care if the hostages die. So that is a unique problem with red teaming a nuclear facility that has active armed pro force. Here at the INL, our on in town facilities don't, those guards are not armed anymore, but out on the desert they are. So that's definitely, but that still doesn't mean, right, that you can't, someone's designing a glove box or a cell or something and mess with it. That's something that you could totally do. Mary posted about TerraPower. Yes, Terra been around for a while. And a few people here at the lab met Bill Gates when he came to town one of the last times. They have an office here in town, and that's actually a thing there. So I pulled some different information. So this is the article you linked here. So it's interesting. Less nuclear waste argument is not something that I had really heard. Um, and okay, they use uranium more, but I'm not familiar enough with how that would actually impact. Uh, um, let me see here. All right, so yeah, I'm not sure about the waste thing. Cheaper construction costs. Okay, I, I'm just somewhat skeptical, but operating at lower pressure. Okay. Um, they don't require the same heavy duty. Maybe, I don't know. Again, nuclear power plants, they're kind of like NASA experiments. They always are cheaper on paper. Um, energy storage is an interesting thing. I had never heard of them storing it in straight up liquid, but that would make sense. There are some experiments here at the lab where they're exploring. There's one that has it uses like essentially like ball bearings. I can't remember what they're made of, but they're the mix of metals in them stores heat really, really well. So something like that also is something they're looking at. So thermal batteries is an interesting thing. It's interesting though. They say everything that was old is new again. Yeah, so they are. You do have a shortened risk of steam explosion. But it's sodium cooled. So, everything old is new again. This is EBR2, which was shut down in 1994. See, this is back when reactors were cheap. This is out at the Materials and Fuels Complex here at INL. This is the silver. It's still there. My understanding is it's empty now. But you can see it from the road. So this was a sodium cooled pool reactor that utilized passive cooling as well in a similar way. So it was shut down. This was a fast reactor for testing purposes. But I know with a lot of different currently liquid metal cooled reactors are kind of in vogue. So there's a few other instances of those. There's a startup in California called Kairos Power, Kairos, which is using fluoride salt, I believe, as the coolant versus just straight sodium. And then the VTR, the versatile test reactor, is a advanced test reactor that is supposed to be being built here at INL over the next, I think, 5 to 10 years or so. It also is I believe it's sodium cooled. I think they decided that. I was involved in one at that time. I couldn't remember if they had determined it. Doesn't say. I think it is sodium cooled, but this is also a fast reactor that's a neutron, testing neutron flux and those kind of things. So interesting. We'll see. I hope it works and it's profitable and everything. What the most important thing to me of this article and everything is where I think they reference it. Let me see here. It's in here somewhere, but they reference that nuclear power is the safest power generation method when compared with gigawatt generated. And it is, when there are instances, they are, they're newsworthy, but in general, they are extremely safe. So that's an interesting one there. And then, yeah, I covered this taser thing, so everybody can comment on that if you're interested. It is one of those things of looking at, what happens when an error does occur, because it always will, given enough instances, right? We can just make it less likely. And, Nathan captured, there's almost like how many different design choices and redundancies were taken with this situation. So, and I commented here, I want you guys to consider when we make a mistake happening. Bad design's part of it. This is one of those times where bad design, you look at it and say, okay, they really did a good job with the design here. So how would you fix it? Nuclear training and procedures matter a lot. So, but cops train a lot with their service weapon and those things. So it's an interesting thing to think about, though, is when we do make an error or mistake, what all do we have to override to make that mistake? So like in this instance, what kind of sensory information had to be overridden, weight of the device, feel, visual system information, pulling from the wrong side of the body. There's a lot of that. And realistically, what it probably means is what we've talked about with human error. This is drawing and firing a weapon for a police officer, same for military, ends up being a skill-based activity. We would consider it as something where it should be second nature. It should be really automatic. You shouldn't have to think about it as much. So this is probably an instance where you have two different schemes at play. You've got your scheme of pulling a firearm and the scheme of pulling a taser, and just one was overriding the information now, but it's interesting to think about. with that and how we could make it better. All right, so going into the actual material here. So what is a human failure event? So human failure events are specific things that will come up in risk assessments in nuclear specifically. So human factors and probabilistic safety assessment. So probabilistic safety assessment is trying to come up with what is the probability different equipment will fail, and then what's the probability that certain equipment obviously will fail simultaneously or in a chain. Human failure events are called out, and they're typically human errors that will have a specific impact on equipment failure. So it's part of that. An equipment failure that would be precipitated or caused by a human error. These are more nuclear terms like the other ones. So unsafe actions are specifically defined and can be called out in different root cause analysis or event analysis things. Important human actions. This is really, no pun intended, this is an important thing to remember. Important human actions are capital I important, H human A actions are actions that are called out in a probabilistic risk assessment or risk analysis that if the human makes a mistake at that point or has an error, then the chance of the core damage frequency probability or release frequency is increased. Doesn't necessarily mean, oh, if the human messes up here, the core is definitely getting damaged. What it means is just the likelihood of that is increased. So they are very, very, they're treated of a higher priority. You'll have task analysis determinations for those to really break down, try to make them safer or design out any risk and mitigate those. So you have two different instances. Risk important is the one I just kind of talked about there. And then deterministically identified are, when you're doing an FSAR, which is a safety analysis report or design control document of your system, these are instances where there's no automation. The human has to take an action. So it's just kind of a process of elimination, right? Okay, the human action is important for this process, so therefore it then becomes an important human action. And here, negative and positive human actions that have, and there are different consequences treated in nuclear. This table sometimes makes it a little bit clearer because they seem to be saying the same thing over and over and over again. Active errors versus latent errors. So this is an important thing as we consider human error. So an active error is an unsafe act or a failure of technological functions or human errors that become the local triggering events that afterwards are identified as immediate causes of an accident. So an operator error, or you meant to hit one button, you hit the wrong one, and therefore something bad happened. Latent errors are more contributing causes, so they are the risks in the instance. They're the tiger got out of the pen at the zoo because the fence hadn't been replaced in 10 years. Like, that's a latent error. That's a risk that has not been mitigated. Another way to think about latent errors, and this is my preference, is the resident pathogen analogy. So you can read through this, but specifically what it's looking at is treating it, it's an analogy alongside healthcare. So resident pathogens that are in a given system, the more likely that an accident will occur. By definition, the more complex the system is, the more pathogens it can contain. Consider pathogens almost like vectors for error. So different ways that the error can come in. If we think about the Swiss cheese model thing, these would be holes in the cheese, and how problematic they can be. So, and this all came from James Reason. He argued that it was more impactful to focus on the detection and elimination of these pathogens rather than active errors, specifically because active errors cannot be prevented 100%. But you can prevent latent errors. You can, through robust design, testing, evaluation, maintenance, whatever, you can eliminate latent errors. Where active errors, people will always make mistakes, but if you create a situation where um, the opportunity for those mistakes is decreased, then you're in a better place. So the analogy I drew is beefing up an immune system versus trying to live in the bubble completely. And obviously, picture from the Bubble Boy episode of Seinfeld. Okay, performance shaping factors. So this is a specific analysis term. So when we talk about HRA, we're talking about modeling human error in specific instances and trying to get a probability of human error. Performance shaping factors are things that impact or modulate or otherwise affect the human error probability. So we have internal and external PSFs. There are probably, I think the last time I saw a count that was reputable, there's probably over 60 different methods for HRA there, and each of them has their own unique set of PSFs. I think SPAR-H is probably the lowest with, I think there's 8 or 10, where there's some that have hundreds. And realistically, there's probably an infinite number of PSFs. We're talking about things that can affect performance positively and negatively. So I always kind of align it with, all PSFs are present at all times. So typical ones could be fatigue, stress, procedure quality, design quality, training, experience. I mean, there's a lot of different ones that could be there, and they're all really present. Like you don't have, so if you have no experience, that doesn't mean that the experience PSF just goes away. It means that it's likely negative effect on your performance in a given situation. Vice versa, if you have a ton of experience, generally we would think that it would enhance your performance. However, the tunneling, we've always done it this way, or those kind of things can also be problematic. So it's context dependent, difficult. The physiological PSFs are a little bit simpler, right? There's enough research out there to, oh, my internet connection is no good apparently. There's enough evidence out there on like fatigue or hunger. I almost said fatigue and sleep, but hunger or impacts, inebriation, how they impact performance in given contexts, that we can probably figure out quantitative impact. It's a lot harder when you get at some methods that talk about workload, for example. I've always looked at that and abstracted term. It's kind of like situational awareness, right? Like, what does that even mean? You really get back, it's kind of like that definition of human error. You really have to start shattering these things into their component parts and say, okay, so when we say something has high workload, what are we talking about? It could be a simple task that to do once an hour, but it requires constant vigilance to maintain. Vigilance is a high workload aspect, but also it could be an increasing, extremely fast-paced series of tasks that is complex. And then the problem, right, for like an HRA is those two things would be treated similarly. When cognitively, those are very different. Those would have very different impacts and very different failure points. Vigilance is a problem for specific cognitive reasons. Complexity is a problem for specific cognitive reasons, and they're not the same. So that's another part of this that you have to consider. I'm going to go into 4 different instances of nuclear errors. One thing you'll find, whether it's nuclear errors or aviation or whatever, You will always find someone's blaming a human. And that, you know, when there's loss of life or property, we want somebody to blame. So blaming an algorithm or a piece of metal isn't usually very satisfying. Doesn't play well in the media. So there's always something there. Fukushima is a little bit of a different case, though. So we'll see that as we go through. And you probably are familiar with these 3 Mile Island, Chernobyl. SE1 might not be. It's pretty famous in the nuclear world, but TMI and Chernobyl are the big ones that you'll hear about outside of that. So 3 Mile Island, there was a malfunction in the cooling circuit of the Unit 2 reactor. The backup system was not initially available because of human failure to restore the system. A pour valve failed to close, but the instrumentation didn't reveal this, so much of the primary coolant was lost through the relief valve. So because of that, and because of the failure to understand the physics of what was happening in the reactor vessel, operators secured inventory makeup, and the residual decay heat in the reactor core caused a partial meltdown and a small release of fission products off-site. There has been no cases of radiation poisoning from the 3 Mile Island or any attributable issues from that. The important thing to look at here, right, is so you'll highlight some specific things. Human contributions to TMI, poor human factors. The valve indicator lights for the pour valve did not show the true position of the valve. That's an instrumentation failure. Limited training. The operators didn't have as much awareness of the big picture of the plant to know what was going on in this situation. And there was too much emphasis placed on avoiding a solid pressurizer. So this is prevent safety injection of the control rods, and there was a tunneling effect or a keyhole effect that were overly focused on that. And because of all these things, there was an over-reliance on a limited set of indicators. So there's no single action, but a series of actions that caused it. So when we look back at that, right, what could have solved this? Doing more robust testing of the interface, some of those characteristics. What design tasks could have helped? Instrument design and usability testing and validation, some of these things that were, let's be honest, hard to do back in 1979, or you didn't even know you had to do them. Overview screens, redundant indicators, SPDS. So these came from actually TMI. These were recommendations called safety parameter data systems. They are essentially overview screens or a series of redundant indications. Some work on integrated knowledge transfer and presentation of that knowledge. But how do you solve a keyhole effect? How do you solve a tunneling on something you're really focused on? People were really good at focusing on specific things. We're not as good at looking at the big picture. So a big thing to think about here is designing for failure. So if you can design for the instance of failure. So okay, failure occurred. You are now in a partial meltdown. What do these operators need to know? What do they need to be able to do? Those are some of the things that are important to help build up the resilience of the human. The Davis-Besse vessel head issue. This was in 2002. So there was a notice that you had through wall axial cracking. So cracking was caused by borate of water. Boron is a neutron modulator, so it is borate of water is commonly used as a neutron absorber as a part of a safety system. So, but it's also corrosive. So the remaining thickness of the vessel head was found to be only 3/8 of an inch thick of stainless steel. That is pretty crazy. So that is so rupture of cladding would have resulted in a LOCA, which is a loss of coolant accident, like what you saw with 3 Mile Island. The reason you get meltdowns is because you can't cool the reactor. So that would be really bad, and damage to control rod drive mechanism. So if your control rods can't insert, you have no way of stopping the nuclear chain reaction. So ongoing evidence of boric acid corrosion, which had systematically been overlooked, and appropriate maintenance had been deferred. They were upcoming to an outage. So deferred maintenance. There was an upcoming plant outage, so they were trying to just make it work till they were damage. It's very expensive to shut down a nuclear reactor to do those kind of maintenance. That led to these workarounds. Safety culture problem. It was found there was a lack of questioning attitude and acceptance of the status quo at plants and persistence of multiple events and no change. That's part of why now, when something goes wrong, you can raise those issues and they need to be treated seriously. But this was a confluence of multiple negative contributing factors and human actions that led to the operating the plant in a degraded state. This is also a big case of organizational failure and some of that management system failure versus TMI had more instrument control problems. So obviously safety culture came out of the David Spetsy stuff. Just culture, which was a thing presented, I think, by Sidney Dekker. Now, those first two we can solve with design. We can work on organizational resilience. We can work on safety culture and those things. We can incentivize those. We can punish them if they don't exist. But those last two, how do you design away the economic realities that shutting down a nuclear reactor costs millions of dollars a day, not to mention grid impacts and those kind of things, and the cost of repairing a vessel head? Building a reactor site is also incredibly expensive. The reactor vessel head isn't something you can just ship off to somebody to repair. You're going to have to expose the core in some way in order to repair that. That's a huge undertaking. So it's, that's one of those realities we need to consider. How do we stop those kind of economic pressures? And then what was the risk? This is the biggest one I always think about is, as people, we're really bad at forecasting events. We're really bad at predicting and projecting our current state into the future. So perception of risk is something we're very bad at. So how do we show that? 2002, computation is pretty strong, but it's not where it is now. So this is where we get into machine learning or AI backed decision support engines. So how do we, if we can predict the risk of some of these things, maybe you can defer that maintenance, given updated technical knowledge or engineering controls or something there. But back then they didn't have the information to make that determination. And I would say back then in that instance, but none of these reactors have that level of sensor clarity or transparency into these systems usually. So I would say nobody can right now, but that's something we need to consider going forward. Chernobyl. So this happened after TMI. Some people, I know me, I always thought it happened before. So this is a unique one. It's non-US. This is running in a completely different reactor technology. And was an odd series of events. So during a test of what would eventually be known as the station blackout. So a unique thing, nuclear reactors generally don't power themselves. They're connected to the grid and drawing power from the grid. So if you can have what's called a station blackout, which is when the nuclear facility loses power and the control room goes dark. There are specific procedures designed to govern what you do in that instance. So automatic safety mechanisms were disabled for the test. This, in addition to a shift delay of about, I think it was 10 hours or so, led a separate crew to run the test that had never been briefed on it. And during powering down of the reactor, the power dropped precipitously to near zero. They were only able to partially restore power level needed for the test, but that placed the system in an unstable condition, which is something they did not know because of a flaw in the reactor design. To restore power, by the way, they had to remove control rods and things that put it in an unsafe condition as well. That's right here. Less than adequate control rods led to boiling of coolant in the reactor, and other factors led to a runaway chain reaction. Because the control rods were too far out, they couldn't stop the reaction, which led to steam explosions, and fires started as a result of incandescent fuel. So the fuel was hot enough, it was glowing. Approximately 5% of the core was vented to the environment. So human contributions to Chernobyl, absent safety culture, that just wasn't a thing, which led to organizational culture problems. There was a poor understanding of its reactor design and technical specifications and its own resilience, and the disabling of automatic safety systems with no redundancy or mitigations in place uh, if the test were to go poorly. Um, if you are interested in that, there's the newer documentary or whatever, but there's a lot of good information out there. Um, Chernobyl, last I'd heard, you can go there and like tour now. Um, I don't think anything can grow there yet. Chernobyl was the only instance of radioactive death immediately that I can recall. Some of the fire department members that were first on site died nearly immediately from radiation. Um, it's still there. Um, they essentially built a shroud around it as it continues to decay and the radiation continues to uh, decay to half-life and those kind of things. Um, so what design changes could have helped Chernobyl? Safety culture. So decision support, contextual awareness of what was going on, a technical competency, testing for failure. I would also add in here just, that kind of understanding the human, right? Putting someone in a situation that they've never been in before and then expecting success. It was just a very problematic incident. Fukushima. So Fukushima is a little bit different, I think, personally. So 40-foot tsunami, disabled core cooling systems, and a loss of offsite power, which is also station blackout. 4 reactors. 3 continued to melt down over the following days. The Fukushima site, I believe, has 11 reactors total. RHR, which is residual heat removal systems, failed, and other supporting system failed, leading to the inability to cool the reactors. Eventually, seawater was vented into the cores, which was able to cool them. However, using seawater ruined the reactors. Yeah, so 3 of the 11 reactors at Fukushima were destroyed. All are still in. So, can you plan for this? This is one of the things I brought up. So, it wasn't the earthquake, which was, I think, a 9.3 or something. It wasn't the earthquake that hurt the reactors. They were actually extremely resilient seismically. Um, and there was a tsunami wall. They just weren't expecting a 40-foot tsunami, which essentially drowned some of these systems with seawater. So, how do you plan for these type of, what would traditionally be called acts of God? How do you plan for these situations that wouldn't ever occur in most cases? Um, one of the big things that I think about is, for those of you that have read Voltaire, um, so Voltaire wrote Candide as a mocking nod to Gottfried Leibniz, who was a contemporary of Voltaire's and who made an argument that this was the best of all possible worlds. It was a religiously derived argument. So Voltaire decided to write Candide, which was a satirical play about somebody who goes through life and consistently has horrible things happen to him. And in that, Candide actually happens to arrive in Lisbon, Portugal the day. So, for those of you not familiar, Lisbon, Portugal had an earthquake. I can't remember when. I think it was in the 1600s or 1500s. I could be wrong. On All Saints Day. So Lisbon at the time, heavily Catholic population. I mean, at the time, I'm sure it still is, heavy Catholic population. So All Saints Day is a big holiday. And so to prepare, the city was preparing for kind of a big festival, big party. Most of the city was in church in these large cathedrals that are common in Europe. Some of the people were out in like a city square environment preparing large bonfires and different things to make food for the festival and things. So this earthquake hits. Um, and this is before seismic engineering, right? So on All Saints Day, this earthquake hits. and a lot of these cathedrals end up collapsing on the people inside, on the first there. Those that can't run out of these cathedrals and is on fire because of all those bonfires that went out of control as a result of the earthquake. So these people smartly run to Portugal. Lisbon is a coastal town, so or coastal city, so they flee to the sea, fire, only to be greeted by a tsunami. So it's one of those instances we have to think about, right? These nuclear reactors have to be able to extreme situations. The grid has to stay up. How do you plan for some of these instances? And so that's why I always think Fukushima is a little bit unique, because it have human it human way. So um they so strong, not against size. The staff was very creative by hunting down batteries and anything else that could be of use. The things that um uh, eventually seawater was vented into the cores to begin cooling reactors. One of the things they should have done was make this decision sooner. The kind of drug their because they knew it would ruin. So that's one of those questions of economic pressures, right? Want to be the guy who vented the seawater or too soon, ruin the reactors when you didn't have to, but you also don't want to be the guy who did it too late. Um, so that's one of the things to kind of consider in this instance. So what happened? Birth flex procedures worldwide. So the staff was very creative by hunting down batteries, pumps, generators, and anything else that could be of use. So they lost all residual heat removal and they lost AC power. So the reactor wasn't powered, which meant all of those pumps and things that are intended to help in these instances were not functional because they had no power. So they were clever and they went out in the parking lot. There was a bunch of cars there, and a lot of them started breaking open these cars and getting the batteries out and wiring them up to power different things. Some of them were able to find pumps, generators of different sizes to, they were trying to pump water out of these facilities so that they could get at the generators and all those. That's what birthed what we call flex procedures. Flex is flexible plant operations. Um, so as a result of Fukushima, there's a lot of different types of steps and mitigations in place, but some of them are, for example, I believe in the United States, no nuclear facility is in a position where if there was such a incident, um, generators, additional pumps, those kind of things cannot be delivered outside of 24 hours. Like I think we have like deployment stockpiles in most major areas, and um, so that's an instance there. We also have nuclear facilities now are building outbuildings, different additional facilities to store pumps, generators, and these kind of things for the such a instance. But the question I want you guys to think about is, what do we expect humans to be able to manage? So Fukushima is like a once in a lifetime event, just like the Lisbon earthquake. At what point do we keep putting this on humans, right? It's a once in a lifetime event. If you do everything right, you're going to be a hero. If not, we're going to haul you in front of Congress and you're going to have to explain why your actions are a root cause to something failing. We need to kind of consider that. And as it's our job in human factors to expect accidents to happen and expect mistakes to occur, human error. And it's our job to try to prevent them through design or support these individuals, uh, with decision support or, well tested, well validated instrumentation or all sorts of different options. Flex procedures are a huge one. We work on this at the lab where we're looking at the risk of flex procedures failing, or what does that do? do flex procedures give you? You can't cool a reactor with, a series of sump pumps that you got from Home Depot. So what are we looking at here? How much time does that give us in these instances to get these pumps back online or various things? So um, that's kind of the work that we have to do now. Um, so it's one of those things I want you guys to consider. The class human centered design in nuclear systems. There's very few ways it gets more human centered than trying to prevent errors that lead to loss of life. So um, just kind of consider that. That's all the slides I have on this one. I thought I actually had merged over the other one. So I'll end this one here. And like I said, I think there's going to be a part 3 there. But everybody kind of throw out your comments. There's a lot of good discussions on the Slack already. Let me know what you guys think about the final and topics that you want to make sure we cover. Um, I know I always hate that in classes when I'm like, I like this information, but I would really like a discussion on how it applies to X, Y, or Z. So let me know if you have any of those. Also, I think I have a reminder on my calendar set to make sure they go out for course evaluations. Um, I'm new to this, so I think it's already loaded with questions, but I'll check, and then I'll make sure you guys get that link or whatever it is out there. Yeah, so reach out if you have any questions directly or if you need anything. Hope you guys all have a great weekend and enjoy the human error slides stuff. So thanks.